I am about to prove that in a room of just a few dozen people, there is a better than 50% chance two of them share a birthday. No tricks, no leap years, no twins. And if you think that is impossible, your brain just fell into one of mathematics' oldest traps. That number of people, by the way, 23. Just 23 ordinary people. You have 30 students in your classroom. What are the odds two share a birthday? Take a guess. What did your brain just calculate? You probably compared your birthday with everyone else's. 29 other people. 365 days. Maybe 8%, maybe 10. That is exactly the mistake. Your brain solved the wrong problem entirely. Mathematics looked at your calculation and quietly deleted it. The question is not whether someone shares your birthday. The question is whether any two people in the room share a birthday. And that changes everything. Wait, if there are only 23 people, where are all these matches coming from? Watch what happens when you connect them. Person 1 connects to 22 others. Person 2 connects to 21 more. Now imagine doing this again and again, 23 times. Your classroom just transformed from 23 people into 253 invisible conversations, not 23 chances for a match. 253 simultaneous chances, each one independently testing for a birthday collision. That is not a small number. That is the entire reason this works. And here is the part nobody tells you. This innocent classroom puzzle protects the entire internet. But we will get to that. First, the formula. Mathematicians discovered a shortcut for calculating this exactly. And honestly, it looks terrifying at first. Luckily, it is lying to you. There is only one part you actually need to understand. Instead of calculating the probability of a match directly, we calculate the probability that nobody matches and subtract from 1. Probability of at least one match equals 1 minus the probability of no match. Person 1 can have any birthday. 365 out of 365. Person 2 must avoid it. 364 out of 365. Person 3 must avoid both. 363 out of 365. Now imagine doing this again and again, all the way down. 365 over 365 multiplied by 364 over 365 multiplied by 363 over 365. Continuing until you have multiplied 23 fractions together. Multiply them all. You get 0.4927. That is the probability nobody shares a birthday, which means 1 minus 0.4927 equals 0.5073, 50.73%. The total number of pairs driving this is given by n times n minus 1 divided by 2. That single expression, n times n minus 1, is the engine. It grows as n squared. Every new person you add brings not one new comparison. It brings n minus 1 new comparisons, all at once. Mathematicians also found an elegant shortcut using one of the most famous numbers in mathematics, Euler's number. The important part is not the constant. It is the n squared hiding inside the equation. That is why the curve does not grow slowly. At 23 people, it crosses 50%. At 50 people, 97%. At 70 people, 99.9%. Quadratic growth waits for no one. Every password you have ever created, every online payment you have ever made, every encrypted message you have ever sent, depends on the exact paradox your brain just got wrong. In cryptography, hackers use something called the birthday attack. They do not need your exact password. They just need any two inputs that produce the same output, a collision. Same formula, same quadratic growth, same counterintuitive probability. This is why modern encryption uses output sizes of at least 256 bits. Cracking SHA-256 this way would require roughly 2 to the power of 128 attempts. That is not millions, not billions, not even more than the atoms on Earth. It is more than the number of atoms in the observable universe. A classroom puzzle running the security of the entire internet. 23 people. Mathematics never lied to you. Your intuition did.